Hello and welcome to our 33rd edition of FSI Fridays. I'm Edwin, live in Boston, joined by
Johansson, live in Charlotte.
Hey Johansson, what do we have lined up today?
Thanks, Edwin, and those in the audience for joining today. We're going to talk about quantum computing and its important relevance to the financial services organization.
Next, we'll hear how it works and see a demo on how customers can get started.
Third, we're going to talk about use cases and how this can be leveraged by financial services organizations and why it's important for financial services organizations to get ahead of this.
Then we'll wrap it up with Q&A.
Today on FSI Fridays.
For those of you watching live or on YouTube, as a quick reminder, we'll spend about 30 minutes on today's topic and leave the last 10 to 15 minutes to address any burning questions.
So please use the Q&A window and we'll monitor for questions during the presentation. If you're watching the recording, feel free to use the comments below to ask your questions.
So let's get started and meet the presenters for today. Johansson, who's our special guest this week?
We're thrilled to be joined by Leonard Woody, a senior consultant as part of our Developer Advisory Services org. Woody, can you share with your audience what your role is at Microsoft in your typical day? We also heard that you had a fun fact that you've been to the Oval Office. I'm assuming that this is probably not from this past January.
Yeah, so I'll answer the first question, get that one out of the way. No, it wasn't this January. It's actually 21 years ago in 2000. I was an intern on Capitol Hill, and we got a West Wing tour, and I got to stick my head in the Oval Office, which was awesome. Typical day for me, I manage about 5 clients in the financial services industry and help them with software development problems ranging from C# to Azure and sometimes quantum computing.
Thanks for sharing that, Woody. We're also joined by John Skerrett, Senior Application Developer Consultant for Microsoft Federal. John, thanks for being on the show today. Can you briefly tell the audience what your responsibilities are? And we hear you have a talent on one side of your body that isn't normally achievable by the average person.
Yeah, actually, I can clap using one hand, but only using my left hand. Can't do it on my right. But I write C# applications and mostly for enterprise clients. And now I've been doing Q# for about 1.5 years.
Thanks. So let's jump right in. Woody, why is quantum important in the financial services industry? We've heard it being used to model climate change and other topics, but why should our financial services organizations take note of this?
One of the biggest one is cryptocurrencies, which is getting a lot of news, these days on the high price of Bitcoin going up and up. But what goes behind Bitcoin is blockchain, the technology that basically tracks all the transactions that are made with Bitcoin. And when we get a quantum computer, and this could be 5 to 10 years, there's a threat there that you could actually use Shor's algorithm to break the cryptographic protocols that are used with blockchain. There's a public key called paid to public key, P2PK, not to get too technical here. And it's something that we should start planning for today because when it comes, it's going to be quite an attack on the financial system if we don't come up with something that's called a post-quantum cryptography.
Thanks for sharing that, Woody. There's a lot of going on with cryptocurrency today. I can only imagine how Bitcoins might be part of that vulnerability. How big of a threat is this?
So to kind of quantify it, they had a study in Deloitte, actually, that came out just in December, and it talked about how many Bitcoins are out there and which of these use the cryptographic protocols that could possibly be broken by a quantum computer. And right now, if we had all the ones that were called the pay to public key, if you see the dashed line, the dashed red line, those are all the Bitcoins that would be vulnerable to this type of attack. And at the current price of $50,000 per Bitcoin, that means that $203 billion is vulnerable within 5 to 10 years if a quantum computer is able to implement Shor's algorithm.
So Woody, let's start by grounding our audience a little bit and helping them understand what quantum computing is. I've heard it's based off this premise of qubits, but how does this all work?
Yeah, so to do this, I find it helpful to draw a few parallels to classical computers. If you were to pop open the devices that are sitting right in front of you and look inside, you'd find transistors. Transistors are just tiny switches that can be on or off, like a light switch. They can support one state at a time, on or off, and we map those on and off to ones and zeros. So the more information and compute power you need, the more ones and zeros you need, and therefore the more transistors you need, which is why today we strive to fit more and more transistors on a single chip without increasing the size. We've gone from computers comprising just 13,000 transistors, the size of a room in the 60s, to game consoles like the Xbox comprising over 5 billion transistors. So A qubit, which is analogous to a bit in our classical computers, is the fundamental building block of a quantum computer. And it can be in more than one state at once, a 1 or a 0 simultaneously through what we call superposition.
Thanks for explaining that, Woody. It's very understandable, so that's great. John, can you talk to us about how that translates into classical computers from a computing perspective? So in other words, why can't we do this stuff on classical computers?
Well, to do that, we have to put a little bit of context around scaling qubits, right? With quantum computing, we achieve exponential increases in computing power. We obtain double the power with each additional qubit that we add. So say we want to simulate a quantum computer on our classical computer. Simulating 20 qubits only requires about 16 megabytes of classical memory. Not too bad. Simulating 30 qubits requires 16 gigabytes of classical memory. And if you go to 50 qubits, that requires not 10 times, but 1,000 times more memory, about 16 petabytes of memory. So adding an additional qubit means doubling the memory required. 230 qubits requires a classical memory of 10 to the 80th bytes. And that's so large, it's larger than all of the numbers of particles in our visible universe. So simulating one operation on a quantum state with a classical computer like that requires longer than the lifetime of our universe. But there are some catches that make quantum algorithms difficult to find. We only get to read out one answer at the end, unlike a classical algorithm. And we need to come up with a clever algorithm for which this can be done, like using the principles of superposition and quantum interference.
So, John, this sounds great, but some of us have heard that quantum computing is probably ways out, and we're still trying to solve that problem. So how can Microsoft and our financial services customers unlock this value and gain access to quantum compute?
So Microsoft has Q# and the QDK, which are open source and available to the broader quantum community. Q# is a universal language, meaning that it can run on any gate-based quantum computer. And Azure Quantum brings the world's most diverse and robust sets of hardware, software, and solution providers, including leading quantum hardware providers such as IonQ, Honeywell, and QCI, and solution and application providers such as 1QBit and Toshiba. Over time, Microsoft will bring our own hardware to Azure Quantum, making it a one-stop shop with continual updates to keep things fresh. Azure Quantum is built on Azure, which brings the familiarity and scalability of the world's computer to quantum computing. So we provide quantum tools and capabilities to make it easy for you to get started. And it's here, ready today to build solutions so you can maximize your impact now and into the future.
That's great, John. A lot of our financial services customers are definitely jumping on Azure, so they should definitely take advantage of this and leverage what they're able to. So speaking of that, Woody, this may sound complicated, but can you share your desktop and show the audience how easy it is to get started?
Sure. Let me go ahead and bring that up. So yeah, I'm here in the Azure portal, and I'll go ahead and show you how to get started with Azure Quantum. So I'll come up here to the search and just type in Quantum. It's the first thing that comes up, Quantum Workspaces. It takes me directly to where I can create and see the quantum workspaces that I've had. And I'm going to go ahead and create a new one right here. And the first thing that I need to do is do a resource group. I've already got one created called Quantum. Then I need to give it a name. I'm just going to call it Q5 since I already have 1, 2, 3, and 4. And won't let me actually do that. So let's just do 5, 5. Someone might have gotten that one. And then I need to select a storage account. And so I'll just do QWoody here, and I'll just say next. Here is kind of the cool part. So I'm going to go ahead and minimize this. This is where I get to select the actual quantum computers that I want to access in my quantum workspace. So I'm going to go ahead and do all of them. This is the 1 qubit provider here. I'm going to go ahead and enable that. I'll take the Honeywell one as well. And I'll take the queued access on that one. And then IonQ, which is actually use trapped ions to be able to enable quantum computing. And then we also have the Microsoft QIO, which is the quantum-inspired optimization that we have available as well, which can give you impact today. Go ahead and press next, put any tags that I would like, just to make sure everything is tagged correctly. And then I can review and complete it. So yeah. Here we are, and I go ahead and press create, and it goes to Azure, and they start the deployment. We can go ahead and watch how it goes. And so while that one's loading and being deployed, let me go ahead and just show you one that I have from before. This is a Quantum Workspace, and it gives you all the different descriptors you need to show how to access it from either the CLI or from Q# or language. Once you do that, you can start to submit jobs to these quantum computers, choosing which one you would like, and start to get results from an actual quantum computer.
Woody, wow, that was pretty amazing. You just went into the Azure portal, you searched for quantum, and in a few minutes, you were able to get really started on a quantum computer. So for our financial services customers that are watching this and want to kind of maybe see a guided walkthrough, what resources do we have to help them accelerate their knowledge around how they can leverage Azure Quantum?
Glad you asked that. So we actually have, and we just released a Quantum Computing Foundations on Microsoft Learn. We'll have the link at the end in the show notes, but there's quite a lot of extensive modules here for you to be able to go through and actually learn how to use quantum computing within Azure, and also some of the concepts behind it. So I encourage you to go there to try to learn how to use quantum computers.
Thanks, Woody, for walking us through that pretty amazing demo. So, John, can you give us some examples and use cases, specifically where there's probably a lot of risk involved? I can see some applications here in financial services, and maybe how this risk can be quantified and what it's working on.
Yeah, absolutely. Willis Towers Watson has been working with Microsoft since 2019, collaborating on a transformation of risk management and insurance. And we're leveraging the capabilities of Azure Quantum to bring advanced modeling tools to them and their customers. Current techniques to quantify risk require a vast amount of computing power. The new modeling techniques are much more efficient in their ability to quantify risk. The process is the same as we use in developing any new quantum-inspired algorithm. Think about how things would run on a quantum computer at scale, and then apply that model to the hardware that we've got now. The partnership is both unique and exciting for Microsoft and Willis Towers Watson.
Willis Towers Watson covers actually an amazing range of services. They're all around, though, the issue of people and risk.
One of the things that sets Willis Towers Watson apart is the use of advanced technology to solve client problems.
Engagement with Microsoft started where we wanted to work with them on the idea of quantum computing, preparing for quantum computing by starting off with what we call quantum-inspired computing today. This is a breakthrough that is going to provide incredible computational power and a different way of really computing.
Risk modeling is a little bit different to the classic big data AI sort of problem. With risk modeling, you're trying to quantify the whole distribution of outcomes. It requires quite a lot of specialism, and the prevalent technique is something called Monte Carlo simulation. Simply put, we roll the dice lots and lots of times and calculate from the resulting outcomes.
Quantum-inspired optimization leverages the principles of quantum physics to solve optimization problems in a faster to higher accuracy.
Currently, we can run sort of realistic models in 10 or 15 minutes. If we can bring that down to seconds, then immediately that's opening up the door to real business value.
What this means for the end user is we give them information and insights that they were never able to have before. The limits of traditional computing just meant that we couldn't analyze certain things. With greater insights, then comes more efficiency and better choices. I love the quantum-inspired computing, partly because of the problems that we're going to be working through with Microsoft today, but perhaps more because of what we'll do in the future. The problems we're tackling today, we'll get some great insights and some great results from them, but there'll probably be things that we haven't even begun to think about today that'll give us future results. That's what's really exciting.
That's great, John. Can you give us another example where FSI, in FSI, where quantum computer can really help as well?
Sure. The Black-Scholes model equation that is shown at the bottom of this slide, and for anybody that doesn't have a degree in math, a simple explanation is that it determines a fair price for options. Now, if you're feeling kind of squirrely, this looks like an equation that you might be able to solve. But pricing can get a lot trickier as these variables turn into equations themselves, where you have to compute multiple paths in order to determine the different outcomes for our other equations. So using quantum-inspired algorithms, we can process multiple variations of pricing models in a significantly reduced time to classical computing.
So Woody, I know that Monte Carlo as the casino in Monaco, but how is this term related to quantum computing? And does this have to do with the roulette or dice, like a game of chance?
It does actually, and that's one of the reasons it's called the Monte Carlo simulation. One of the ways that we try to, within the financial services industry, predict how assets will get either rise or go down lower is to use Monte Carlo simulation through probabilistic models with math. And this here graph shows you a particular asset price and all the different ways that it could possibly go with a Monte Carlo model. Now, if you could imagine a portfolio with thousands, if not millions of assets, going through all these simulations takes a lot of computing power and many thousands of hours. With quantum computers, we can actually do that much quicker. And we're able to predict possibly things like black swan events, like the Great Recession, or even, have things like the pandemic within our models and how that's going to affect them very quickly. And not only that, when you try to rebalance a portfolio, you want to do it as often as possible based on today's risk and news. And quantum computers can actually run these Monte Carlo simulations quicker once they become available.
And as well, it allows you to compute multiple paths so you can rebalance a portfolio from multiple horizons. That can lead to significant savings if your rebalancing costs a lot of money to do.
Woody and John, I mean, that's really exciting. It sounds like quantum computing can help predict a lot of, things that might happen in the future, such as the next pandemic or the next recession, and hopefully we can, prevent that from happening. So Woody, these seem really cool, but now that we know how to get access to quantum compute, it still seems like a really big challenge to find different solutions. Is Microsoft doing this alone, and who else is working on this, and how are we working together?
That's a great question. This is quite a industry, if not world problem that we're going to have to work together on. And Microsoft has created the Microsoft Quantum Network to enable us to work with not only partners in the commercial arena, but different customers and even in academia to be able to create the quantum solutions that we need for today's problems. As you can see here, we have quite a wide swath across those three areas, and we're adding more as we speak. So I encourage people that are watching this to get in touch with us and join the Microsoft Quantum Network.
The Microsoft Quantum program is a global scale program focused on enabling commercial scale quantum computation. It's really about bringing quantum impact to people today and tomorrow.
Quantum computing has the opportunity to make an impact on the world right now in a revolutionary, game-changing way.
We're focused on developing every element of the quantum system, an end-to-end full-stack technology from the algorithms to the software stack to the hardware itself. To reach a commercial scale quantum computer, it requires revolutionary discoveries across physics, computer science, mathematics, materials science,
all of which have to come together to make topological qubits and multi-topological qubit systems. We have a team that's spread across 8 labs around the world. Although we're spread out, we are one team working towards one goal.
Building a quantum computer is a huge task. It's all the way from the software, all the way down to where we control the quantum states that makes up the qubits.
Here in the lab, we have fabrication technologies, nanotechnology, that allows us to turn dumb materials into smart devices.
The Microsoft Quantum program allows us to dream big. We need to dream big.
Azure is the world's computer. You have access to the tools, services, and solutions in a very familiar environment. And with Azure Quantum, we're bringing quantum solutions forward to that environment. We're bringing quantum impact to your fingertips. We're working with enterprises and companies around the world, energy optimization, risk and financial analysis in medical diagnostics, to identify where quantum solutions will bring about impact for their businesses. A great example is Case Western Reserve University.
We're working with Azure Quantum to optimize the way that people get MRI scans. Patients have access to faster and better MRI scans in a way that wasn't possible before.
We can make those scans up to 3 times faster by using quantum solutions on classical hardware today.
The really high-level scientific goal is to be able to solve problems that we can't solve today.
Azure Quantum enables every developer, every person, every enterprise to really tap in and succeed in their businesses and their endeavors with quantum solutions. And that's incredibly powerful.
So, John, what's the call to action for our financial services audience here? How can they get started and get more information? I think you have a set of links and resources, which we'll be sure to link to the bottom of this video. But how do they get started?
Well, the key takeaway is that quantum computing is real, it's here, and it's already providing insights to the financial industry. People from any sector or department can use the links here, also in the show notes, to start leveraging the power of quantum computing on Azure Quantum today.
John and Woody, thank you for sharing your time and perspective. I'm positive our viewers have learned a wealth of valuable information. What we've learned is what quantum computing is and how it's having an impact now and offer impact in the world of finance in the future.
We also got to see a demo on how easy it is to get access and start your journey with quantum computing. And we even discussed some examples and case studies such as risk analysis and the tough problems that finances face today that quantum can solve.
And finally, we learned that the key to all of this is that Microsoft is not doing this alone. And in order to have high level importance that the world needs from quantum computing, there needs to be an active community of developers, global workforce, and a vibrant ecosystem.
Really great stuff. Thank you, John and Woody, for joining us. So Edwin, let's move to Q&A. What are some of our viewers asking?
All right, thanks. So we have a question here. What are these quantum computers made out of, and how are the components different from building a classical computer? Woody, do you want to take this one?
Sure. Physicists are working on different ways to create quantum computers. One way is called trapped ions. We actually take ions themselves and trap them with lasers and actually shoot them in there to create what we call gates, which are just basic logic operations. There's also superconducting qubits, which are put onto a chip, and they actually have to keep them at very, very low temperatures to be able to stop things that we call decoherence. And there's other ways that we're investigating here at Microsoft as well. So there's a lot of different ways to go at it. There's also photon computers as well. Anything that shows quantum mechanical phenomena can be used. And really that's the race today, is what is the best way to build these quantum computers hardware-wise? We've got the algorithms, we've got the software. What's our next step for hardware? So great question.
Thanks, Woody. We've got another question here from Anonymous. Are quantum computers going to completely replace traditional computers? Is there going to be a quantum phone? John, do you want to take this one?
Sure. No, quantum computers are definitely not going to replace traditional computers. There's probably no reason to have a quantum computer in your pocket. Quantum computers are really good at answering questions that model the way that nature is constructed. So molecules, materials, things that require lots of information. This is why quantum machine learning is so interesting, because it's a leap into the future of the possibilities for quantum computing. But for right now, no.
Great. I have an awesome question here. I'm not sure who wants to take this. Is this related to Quantum Leap?
Great show. Love that show. We were actually talking a little bit about it right before the show. I don't think the only leaps that we will be taking is hopefully the amount of time that it takes to actually get a quantum computer. Right now, estimates are from 5 to 10 years. I'm hoping it's 5 years before 10. But still remember that we have quantum-inspired optimization algorithms today at Microsoft Quantum that actually will solve a lot of your financial problems today. So yeah, I hope there's a quantum leap in our future. We'll just have to wait and see.
To add to that, there's a quantum leap happening every year. A lot of people are familiar with Moore's law, which states that transistors on a chip duplicate every 18 months. We've got Nevin's law for quantum computing, which states that quantum computing machine qubit densities double every 2 years. So each year we've pretty much gone on and said that we've developed a higher strength of qubit or more qubit density. And that alone has provided leaps and bounds in the last 3 to 5 years.
Thanks, John. We've got time for one more question. This one is, how else can quantum be used from a security-focused purpose, as our financial services customers have security and compliance top of mind? Can it enhance security? Who wants to take this one?
Yeah, go ahead and take that one. It certainly can. There's a whole area called quantum communication, actually. And we can now come up with quantum cryptography protocols in which we know if a hacker has listened in on our message. And that really gives us an advantage because a lot of times today we don't know until after the communications have happened that a hacker has actually been, or a nefarious party has been listening in on our communications. So once we get the quantum communication going, and we have some prototypes right now, that could really give us an advantage on not only securing our communications, but knowing immediately if someone's listening in.
Thanks for answering that, Woody. So it looks like we're out of time. Thanks again for attending via YouTube or watching live and asking questions.
If you haven't already, be sure to subscribe for FSI notifications and invites by visiting aka.ms/FSI Fridays.
We're also open to constructive feedback. Please send us your comments and suggestions at aka.ms/FSI Fridays feedback.
Be also sure to catch the recordings of our previous sessions on our FSI Fridays YouTube channel at aka.ms/FSI Fridays recap, where you can also post any follow-up questions that weren't covered today.
And don't forget to subscribe to our YouTube channel.
So Edwin, we have an awesome rest of the lineup for Modern March. Why don't you give an audience a preview of what's happening over the coming weeks?
Most definitely, Johansson. So next week on March 19, we'll be joined by key stakeholders from NASDAQ to discuss some of the key observations and lessons directly from the field as NASDAQ helps address market transformation and technology evolution for its 300-plus market infrastructure and market participant clients.
Then on March 26th, we're going to talk about how insurance carriers are struggling with demand to optimize their risk model operations and how they can gain valuable insights from their data and address the ever-changing regulatory demands. So we'll discuss how to address these challenges with cloud compute.
You won't want to miss it.
Thanks, and see you next time
on FSI Fridays.